The cylinder head is not simply a cover. It forms the top of the combustion chamber, seals combustion pressure, routes intake air and exhaust gas, carries the injector, transfers heat into the coolant, and controls exactly when the cylinder can breathe. A valve that misses its seat by only a small amount can lose compression, overheat, and burn. In this Aspeling Machine Rescue lesson, we will identify every critical cylinder head and valve train component, follow the forces that open and close the valves, compare the metals used, and diagnose why valves and cylinder heads fail. Start at the casting. The deck face clamps against the head gasket and cylinder block. Above it are the combustion face, intake port, exhaust port, coolant jackets, oil drillings, injector bore or injector sleeve, and the valve seats and guides. On top, the head supports spring pockets, rocker pedestals, or camshaft journals, depending on the design. The valve cover keeps lubricating oil inside, but the cylinder head itself must contain combustion pressure, coolant, and oil without allowing them to cross. Cracks commonly begin around highly loaded areas such as valve seats, injector sleeves, glow plug bores, pre-combustion chambers, and narrow bridges between openings. The intake valve controls fresh air flow into a diesel cylinder. As the piston moves down on the intake stroke, the cam opens the intake valve and pressure difference fills the cylinder. The exhaust valve opens near the end of the power stroke so cylinder pressure can blow down. Then the rising piston pushes the remaining gas out. The cam profile determines opening point, closing point, lift, velocity, and acceleration. Both valves can be slightly open around top dead center during valve overlap, using gas momentum to improve scavenging and cylinder filling. The spring closes the valve and keeps the follower in contact with the cam. It does not decide the timing. The camshaft and its drive do. There are several actuation layouts, but the force path is always traceable. In an overhead valve engine, a cam in the block lifts a tappet, then a pushrod, rocker arm, and sometimes a valve bridge. In a single overhead cam head, one camshaft works the valves through rockers, fingers, or buckets. A double overhead cam head normally separates the intake and exhaust camshafts and can use direct buckets or finger followers. Hydraulic lifters or lash adjusters use engine oil pressure to remove running clearance automatically. Many heavy-duty diesels instead use an adjustable mechanical lash, because the exact cold or hot clearance is part of the engine calibration. Heavy-duty engines often use a rocker shaft and valve bridge. One rocker can press a bridge that opens two intake valves or two exhaust valves together. Bridge adjustment is critical. If the bridge is not level, one valve carries more load, one seat may not seal, and the valve train can suffer uneven wear. Some cylinder heads also carry injector rockers or engine brake hardware. A compression release engine brake changes exhaust valve operation when fueling is off. Near the top of the compression stroke, it opens the exhaust valve, releases the compressed air, and converts the engine into a power-absorbing air compressor. That extra event must never be confused with normal exhaust timing. Follow the valve from bottom to top. The valve head contains the face and margin. The fillet joins the head to the stem. The stem runs inside the guide. A stem seal meters the small amount of oil needed at the guide while limiting oil entry into the port. At the top, two collets or keepers lock into the valve stem grooves and hold the spring retainer. The spring provides closing force and prevents valve float or bounce. Some engines use inner and outer springs for control and redundancy. Exhaust valves may use a rotator or rotocoil, turning the valve slightly during operation to distribute heat and deposits around the seat. Material choice follows temperature, strength, corrosion, wear, and heat transfer requirements. Intake valves run cooler and commonly use heat-treated Martensitic alloy steel. Exhaust valves face much higher thermal and chemical loads, so they may use austenitic heat-resistant steel or a nickel-based superalloy. A bimetal valve can combine a heat-resistant head with a wear-compatible stem by friction welding. Hollow exhaust valves may contain sodium, which moves heat from the hot valve head toward the stem and guide. Valve faces can be induction-hardened or hard-faced, while stems may be nitride, chrome-plated, or coated. Never judge interchangeability by size alone. Alloy, heat treatment, coating, and magnetic behavior can differ. The valve seat is both a gas seal and a heat transfer joint. When the valve closes, its face must contact the seat evenly around the full circumference. Much of the exhaust valve's heat then flows through the seat insert into the cooled cylinder head. Seat inserts are commonly hardened or sintered powder metal alloys chosen for hot wear and corrosion. Guides may be cast iron, sintered iron, or bronze-based material. Too much guide clearance allows the valve to wobble, damages concentric seating, and pumps oil. Too little clearance can wipe away the oil film, seize the stem, and hold the valve open. Correct guide geometry must come before final seat machining. A burnt valve normally begins with incomplete seating. If lash is too tight, if the seat has recessed, if carbon is trapped on the face, if the guide and seat are not concentric, or if the stem sticks, the valve cannot transfer heat evenly. Hot combustion gas then escapes through the smallest leak. The leak acts like a cutting torch, creating a narrow hot channel, eroding the valve face and seat until compression collapses. Overheating, incorrect injection timing, overfueling, a distorted spray pattern, restricted exhaust flow, and cooling system faults can increase the thermal load, but a healthy valve still depends on full seating. Replacing only the burnt valve without correcting the seat, guide, lash, injector, or cooling cause guarantees a repeat failure. Other patterns tell a different story. Excessive lash hammers the tip and rocker, increases noise, reduces effective lift and duration, and can fatigue components. A weak or broken spring allows float, bounce, or piston contact. Incorrect cam timing, an overspeed, a failed belt or gear drive, or excessive head machining can cause valve-to-piston impact and bend the stem. A worn guide can fracture the valve at the fillet or keeper groove. Seat recession gradually removes lash until the valve stays off its seat. Cracks between seats or around an injector sleeve can leak combustion into coolant, coolant into the cylinder, or fuel into the cooling system. Read the damage pattern before ordering parts. Cylinder heads are commonly cast from gray cast iron, compacted graphite iron, or aluminium alloy. Cast iron provides stiffness and hot durability. Aluminium reduces mass and transfers heat quickly, but expands more and is sensitive to overheating and surface damage. The head gasket must seal combustion, coolant, high-pressure oil, and oil drainback paths while the head and block move during every heat cycle. Multi-layer steel gaskets need the specified surface finish, flatness, bolt condition, lubrication rule, torque sequence, and torque angle procedure. A new gasket cannot correct a warped head, low liner protrusion, damaged fire deck, pulled thread, or incorrect surface finish. Diagnose before stripping. Compare cylinder contribution, cranking compression, leak down results, exhaust temperature, valve clearance, rocker movement, blow-by, coolant pressure, and oil or coolant contamination. A bore scope may show a clean steam wash cylinder, impact marks, or a damaged valve edge. Air herd at the intake during leak down points toward the intake valve. Air at the exhaust points toward the exhaust valve. After removal, pressure test the head and inspect the deck for flatness and surface damage. Crack detection must match the material. Magnetic particle methods suit ferrous castings, while dye penetrant is used for non-magnetic surfaces. Use the OEM procedure and acceptance limits. A professional cylinder head inspection is measurement, not appearance. Measure valve stem diameter, guide bore and working clearance, valve face condition, margin thickness, overall length, tip wear, and stem straightness. Check seat runout, contact width, contact position, and concentricity with the guide. Test spring free length, squareness, installed height, and load at the specified height. Inspect retainers, collets, rotators, rocker shafts, bushes, bridges, cam journals, injector sleeves, and sealing faces. A vacuum test can confirm the finished seat seal, but it does not replace dimensional inspection. Any limit, seat angle, protrusion, torque, or reuse decision must come from the exact engine manual. During assembly, cleanliness and sequence protect the work. Clean every oil and coolant passage, confirm plugs and injector sleeves. Keep valves matched to their verified positions when the procedure requires it. Lubricate stems and valve train contact points with the specified product, and install seals with the correct protector and tool. Verify keeper engagement, spring orientation, bridge setting, lash, injector adjustment, timing marks, and manual crankshaft rotation before starting. Valve springs store dangerous energy, so use an approved spring compressor and eye protection. Replace torque-to-yield fasteners and single-use seals where specified. The rule is simple. Understand the force path, prove the sealing geometry, and never guess the specification.